Good morning.
Nice to see you all. Right. Here we go. It is 9:30 on this Monday morning. Welcome to Neuroccino. Today is going to be a very, very special Neuroccino because Victor is going to present for us, and he's going to present for us for the last time after 3 years of being a regular. He is finishing his PhD now, so we have to say goodbye to Victor, sadly. But he's doing one more Neuroccino for us today, going out on a splash and out of his comfort zone. Good man. Yeah. We're going to talk about the cerebellum today. Victor, if you want to share the link to your paper.
Yeah, the die.
Perfect.
And yeah, so, well, yeah, it's my last Neuroccino, and I was hesitating between either something about the brain, which is like on par with what we do usually, or maybe some astrophysics, which is on par on what I do for Neuroccino usually, which is not super on about the brain. And I thought, yeah, I just talk about something that I think is super interesting, but I don't know much about, and I want to learn about. So I went with the cerebellum, and I just pick a recent review, or somewhat recent. It's been published, I think, in 2018, so a few years ago already. But yeah, I gave it a go, and I wanted to read about it. So I'll share my screen now. All right.
Prediction of movement and cognition. I know at least one person in this audience who knows about predicting movement.
Okay, so that would be nice to have like some feedback about this, because actually it's I just realized that it will be pretty hard to present in detail, because there is next to no figures, or like the few figures here and there, but it's mostly text. It's really well written, so if you want to have a go for this kind of thing, it's well written. It's interesting. Lots of well-organized thoughts in this paper, and the critics that like with the self-awareness about the critics, about the different ideas that they have. It's a nice paper, I think. And so yes, let's start with understanding the cerebellum. And one thing that is very important with the cerebellum is that it's been mostly studied in the framework of its importance in movements and motor control, motor learning these kind of things. Historically, because it was the most obvious thing that you could find about it. And one thing that was shown was that it's, well, shown, or at least hypothesized, is that the cerebellum works as probably as a kind of predictive machine that is trying to, based on the input that it receives from the cerebral cortex and from any kind of sensory input it receives, it can create a model, like an internal model of the subject, the person who has this specific cerebellum, and of the world that this person is interacting with. And so it can make short-term prediction about what's going to happen. So for example, it will be able to tell you when you are moving your hand and trying to grab something, it will tell it, and you will know that you are supposed to grab this thing at that moment, and you are seeing your arm moving this way and grabbing at that way. Well, if everything goes right, well, the prediction should match, that is you have in the cerebellum, should match what happens, and this is what is normally doing. But when things does not go right, for example, your hands slip or doing something, there is some kind of error, and that difference between the prediction and what happens, or if the ball is retracted, this error is another part of the functioning of the cerebellum, is the sensitivity to the error between what was predicted by the cerebellum and what actually happened. And this is very important for all kind of learning, because by comparing what you expect with what actually happened, you can try to refine and tune either the prediction or the motion, or both, more probably. And so, yes, so I think there was, sorry, I need to move the thing from Zoom that you can't see on my screen, but it is always annoying me when I'm presenting. All right, so I think there was a forward model here. So this is just the classic thing that we can see, the classic model that we can see with the cerebellum. Like, you have the cerebellar cortex here, and you have all that is around working on, like here it will be, for example, the a motor control thing. So you have the motor cortex that sends information to the motor system, but also to the pons, and then the cerebral cortex. You also have all the inputs and outputs from the environment, also sending information to the cerebral cortex, creating a forward model that will be compared to what's actually happening and everything, and sending back to the deep cortical nuclei, where it can be compared to the actual input and output, and creating an update that goes back to the motor cortex. And so it's a whole loop, and it works. So it's supposedly, the thing that is important, it supposedly works with motor control and motor tasks, but also probably with other non-motor cognition thing. So it's a cognitive task or cognitive situations. So this is a big part of the paper, which is about, so it started to talk about the so yeah, I didn't take it in really in right order, but I started talking about the functional neuroanatomy of the cerebellar interplay, things that we observe a lot of things that are similar between the cortex from the brain and the cerebellum. There is a functional lateralization of the cerebellum. There is quite a nice a nice mirroring of a lot of the part of the cerebral cortex onto the cortical the cerebral cortex, and so, well, with exception from the primary visual and primary auditory cortices, I think. And well, this plus the fact that it has a lot of afferents and efferents from the same parts to the cerebellum, from some cortical area to the cerebellum, like this, it really is a strong indication of, well, a strong, it's a good, it's a good way to say that it makes sense to have in the framework of the cerebellum as a forward model, as a predictive machine, if you want, as it will require input and output from each areas that it is working with. And so, yeah, this is very schematic, but it's get the points across, I think. But what was interesting to me was also, well, so this is really interesting, and it goes into details about all of this. But so one thing that interested me also was that it tries to say that this kind of predictive power from the cerebellum can probably also be the explanation on why the cerebellum is used by non-motor processes, because this is something that have been shown again and again, is that in non-motor cognitive processes, you have also activations of this in the cerebellum when you do neuroimaging studies. And so the question is, why exactly, what is the cerebellum used for exactly in these cases? And well, the hypothesis is that it's probably, well, maybe, it's not sure, but it's probably something that is akin to prediction too, just not for a specific motion, but for how you expect the situation to go in the cognitive framework that you are working in. For example, and this is why I think it might be interesting to a lot of people here, in language functions, especially, it's been shown that when you have, they're studying a few studies, but one that struck me was, they say that when you have sentences where you can infer the next words, or the words in the sentence that comes at some point, but you are actually replacing it by another word during the task, it shows a much stronger activation in the cerebellum than when you do it with a sentence, when the person reads a sentence that is exactly as expected. Like, for example, you show a cake, and the sentence says, "The boy eats the cake." Well, that's normal. But now you show a cake and you say, "The boy eats the bowling ball," then suddenly there is something that does not work. And that actually is, you instinctively really know that there is, like, oh, something does not know. There is the problem. And this problem is likely related to how the cerebellum was trying to predict the next sentence. The next part of the sentence. It's probably not as simple as that, or honestly, it's probably a lot of interplay between all the language regions and the language network and the cerebellum, but it certainly does play a role. And so they go in long lengths into explaining all this, and all in different way they tried to do it. Oh yeah, there was also a nice other experiments that they did themselves here, was to use TMS to act on the cerebellum, and to check. I think it was somewhat. Oh, actually, I think it was something like as just what I just said. I just need to reread this like very quick. Oh yes, it was the speed at which. So there was the picture with, for example, a lot of different objects, I think, and when there was, for example, the sentence saying like the boy eats the cake, and there was a cake in the middle of the picture with among the other things. And so in normal condition, when the word is congruent with the last word is congruent with the image, the participants could really quickly focus on the part of the image that were congruent with the with the sentence. And it took a little bit more time when the last word was not congruent with the rest of the sentence. Let's talk about the boy eats the bowling ball. And so, all right. And the thing is, when they do TMS on the cerebellum, actually the time it takes to focus on this image on the picture, it's the predictive aspect from the congruency between the word and the sentence, the advantage is lost. So it's basically the predictive power that you had with the cerebellum and with the congruence between the sentence and the word that helps you focus directly on the right item on the picture. Well, this is lost when you do the TMS on the cerebellum. So it's another thing saying, all right, so this this predictive power from the cerebellum is something that is probably very useful for language. And so they talk about dyslexia and all that kind of things that are probably related to this part of the brain and the sensitivity of error and the prediction modeling of the cerebellum. They also tackle a little bit of the problem with the possible social and cognition and affective processing that may involve the cerebellum. For example, in any situation you are in, you usually require some kind of prediction of how things will go in a conversation, or just with seeing nonverbal cues and prosodia and something like this, about what's going on in the interaction with people you are in conversation with. And so this, they say that there have been some evidence, nice evidence, at least in the case for people in the spectrum disorder, autism spectrum disorder, autism disorder spectrum, rather, I think it is, that are showing a disrupted connectivity, like functional connectivity in the cerebellum, that have showing in like gray matter differences in the cerebellar cortex compared to controls. And so there is something here that is important too, and that needs to be more that needs to be more researched. But the big problem is that usually there is very few studies right now about these things specifically. You can aggregate a lot of data from neuroimaging studies, doing something that is related to what they are looking for here, and that have images of the cerebellum, but there is very few specific tasks to test this right now. So this will be a big area of research in the future. So they also talk about a bit of the schizophrenia in these parts, because they're saying that in case of schizophrenia, the mismatch, the potential mismatch that there would be between the cerebellum predicting a situation, even having a proper internal representation of the participant, of the subject, and the outside world, and the prediction of what's going on. If there is a mismatch between the thought process and this prediction, that would be a very ripe environment for any type of hallucinations and problems that the schizophrenic patients can face. And so this would be another line of inquiry. So here the evidence, they say, is a bit more heterogeneous. So it's a bit harder to say exactly what's going on, but it's still a very interesting way to inquire things. Then, well, most of the other part of the paper is much more theoretical, and they come back on a lot of concepts. But yeah, that's the gist of it. I know I've been pretty vague, but for me it's very new. So I hope I got your attention on this, and I just wonder if you have like something to say, and if you are also interested in these kind of things.
Thank you, Victor. Great topic to choose. Wow, hands are up. Valentina.
Hi, Victor. Thank you for this paper. It's really interesting. I already knew it. And I think cerebellum is quite an interesting and a popular topic. I was wondering, just a thought. So the predictive functioning of the cerebellum happens within a network, right? Of feed forward information that don't arrive directly to the cerebellum, but are processed or filtrated by the pons. So what's the advantage of having a sort of like homotopic map of the cortex onto the cerebellum, if the function is anyway it happens in a network?
I mean, I don't exactly get the problem here, because if you have, well, when you're telling that it's happening anyway, what is happening anyway exactly? What the function itself, or the I didn't quite get what you meant.
So if you go to if you share again the paper.
Yeah, sure.
And you go to the image of the representation of the cortex onto the cerebellum.
Yes.
Right. So what's the advantage of having such a specific representation of the cortex if anyway the function it doesn't happen with a like one-to-one relationship between that specific region of the cerebellum with the cortex, but it's something more general because it happens for motor, language.
Okay. So to me, as little as I know, but I can try to answer this. But the thing is, the cerebellum, just to get one step back, cerebellum has a very homogeneous cytoarchitectonic cellular architecture, if you want, with a lot of repeating and the similar microcircuits all over it, which was supposed to be able to do this kind of prediction. But if you're talking about a specific function, I expect that you need to tweak these networks to work specifically for this function. And so that would make sense that you'd have this area that has been tweaked to properly predict a like language that would be slightly different, and so it's more specialized to other area, to one function, and so slightly different to other areas. So you need to have a proper mapping between each part of the brain. It really, to me, who's actually been doing artificial intelligence on a computer before really diving into cerebellum, it really looked to me as something close to an artificial neural network trying to do prediction of an output based on an input. And what I saw there was almost so like like artificial neurons that you tweak in your model, in your artificial and in your AI model, you'd have the weights of all the well, let's say the connections that helps to do the prediction that would be stored in an area. Here they are stored as synapses and strengths of synapses of connectivity between neurons. And so they would be very specific to a type of task. And that would explain why you have very specific areas doing very specific, connected to specific functions. Well,
so this will suggest modularity of the predicting ability of the cerebellum.
Yes. It's like it would be made to do something quite precise in terms of prediction, but the prediction itself need to be tweaked and to be refined, and so it need to be defined in a specific area. Well, also the one thing that I just want to add at the end, that at the end of the paper they say that a lot of this is still putative, and we lack evidence that the cerebellum is only doing prediction. It's a good framework to work on and to have hypotheses, but maybe the cerebellum is doing much more than prediction on error fine-tuning and stuff like that. So it's still
that's why I'm puzzled by the modularity of the cerebellum, because making prediction it's not easy. It's not an easy task. It's not simple. So using like compartments to do this, it wouldn't be efficient.
I mean, I don't know about that. Also, you have to remember that the prediction made by the cerebellum is probably just a little part of the whole prediction thing that may happen. It's still connected to the whole cerebral cortex, and so it's probably more about the cerebral cortex outsourcing a little bit of its computation in terms of prediction to the cerebellum, but still doing a lot of the actual processing.
Yeah, but again, like in making prediction, also, for instance, let's take motor functioning. In making prediction of the motor functioning, it's not only motor cortices, like related to movement, that play a role, but also like the left hemisphere, and also language networks. So they would have to be activated also onto the cerebellum, but for motor functioning, not language prediction, you know?
I'm not following.
So like in predicting a motor behavior, like the outcome of a motor behavior, you would need the input from other cortices, other networks that are not only the motor one.
Not necessarily, I think.
Depends on the task.
Yes. But one thing just to come back to what you're saying, one thing I would be interested in is saying what's happening if you are doing a task that requires multiple things at the same time. Because usually when you're doing neuroimaging, you have a very specific task and you want to have a very specific activation in the brain. And so I guess this is a bias here.
Okay,
Maybe if you are doing something that requires like not just like grabbing something, but also grabbing something because you are told to grab something in this way and blah, 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 and activating multiple networks at the same time, maybe you'll get...
Also, only the presence of an object, for instance, that would trigger something else, the knowledge of the object, the knowledge of what to do with the object, what's the purpose of the object. And this is not just a motor network.
But I think it's more of a general problem with neuroimaging studies. I say problem, it's not true, but it's like a limitation that we have is to test it. It's not just for the cerebellum, for the cerebral cortex too. To test something, you usually have to reduce it to the bare bone of what it is to exactly see where in the brain it will activate, but actually you won't see the whole network, because if you want to have a like real life thing happening, I think it will take.
So, yeah, this complexity is not reflected onto then the results from functional imaging.
Yeah, completely.
Yeah.
I love how you just single-handedly led a discussion that brought us to the end of our time.
Sorry.
Oh yeah, right.
Are there any questions that are burning at this point? No? Okay, great. In that case, thank you so much, Victor, for all the work that you have done for us over the last 3 years. Well done. You definitely gave the majority of the Neuroccino presentations over the years, and we learned a lot from you, and especially from having a very different perspective coming from you being a more on the engineering physicist side. So thank you so much, and all the best for your future. It's very exciting, new things to come.
Thank you.
It was a pleasure working with you on all the levels, and best of luck for your Viva end of the month.
Yeah, thank you very much.
Everyone else, thanks for coming. Have an exciting week in science, and we shall see you next week. Bye.